Hey, welcome. Today we're going to be talking about how a moving magnet can cause electricity to flow in a coil of wire. So literally this, as it rotates, it's shuffling electrons around in different directions depending on how this is rotated. And you may think, that's moderately interesting. And I would say, wait a second, this is the foundation of our modern society, right here. This is more important than people realize. And that's because we're basically getting electricity from this rotating magnet. If you think about it, you're converting mechanical energy into electrical energy. And this is the very foundation, very basis of how we can do electrical generation. Or the reverse, using electrical power to run a motor. So there's this very deep connection with electricity and magnetism, and that's what we're going to be looking at in more detail today. I have done a previous screencast on the right-hand rule, so to better understand what's going on, I'm going to be using the right-hand rule for magnetism. This up here is an example. I've talked about the right-hand rule previously. I'll put a link to that lesson in the upper right in case you want more information, although I will go over it here. And this is the right-hand rule for a current-carrying wire. And I'll put a link to the second lesson as well up in the upper right in case you want some more background information. But I'm going to be using that here, and I'm going to talk you through the major ideas. So the next major concept we need to talk about is something called magnetic flux. And magnetic flux, first of all, don't get intimidated by Greek letters. This is phi right here, and so it's a measurement of the magnetic field passes through a given area. So if we have an area right here, and this is a little difficult to visualize because I'm trying to show a three-dimensional process in 2 dimensions here, but if you had an area right here and some magnetic field was going through this area, that amount of magnetic field that's passing through here would be this magnetic flux idea right here. So that's what we mean by magnetic flux. It depends on the magnetic field, how much magnetic field is passing in that area, and it depends on the area. It also depends on the angle at which we are measuring this, right? If you take a look at this example here, you would get the most amount of magnetic flux based on the orientation of the area over here, the sort of pink rectangle type thing, parallelogram type thing. Over here, you would get no magnetic field that would be passing through, and it just depends on the orientation. So there is an angle involved that we need to be careful with. And an angle is always measured in reference to something else. So what our reference line is going to be when we measure these things is going to be at the normal to the magnetic field right here. So this is actually going to be a 0-degree angle if we're measuring it. In other words, the line that we're measuring from is the exact angle. So there's 0 degrees here. Let me show you another example. This is our reference line. This is the angle that we have in reference to this reference line. Over here, we would have cosine of 90 degrees. Again, I'm trying to draw this in 3 dimensions here, so you could argue that, hey, that's not 90 degrees, but if you just try to roll with it in sort of a 3-dimensional sense, hopefully that makes sense. Over here, you've got cosine of 90 degrees, that's going to be equal to 0. And at this point, I do need to mention that there is a magnetic flux unit called the Weber, and that would be Teslas per meter squared. Alright, so that's what we mean by magnetic flux. Now that we know something about magnetic flux, we can take a look and think about what would happen if we had a coil or a loop of wire and we rotated it inside a magnetic field. Like if you had a strong magnet over here, strong magnet over here, and you rotated this like in this direction here, I want you to think about, would your magnetic flux increase or decrease as this loop rotated to a more up and down orientation right here? What do you think? Well, I hope you can see that as it rotates from this position to this position over here, the loop is going to have an increased amount of magnetic flux flowing through it. Alright, and let me show you another way to visualize this. This is what we had before. This is like our initial. This is our final. And before we move on, I do need to talk about a notation system. If something is going into the page, because again we need to describe 3-dimensional processes with only 2 dimensions, like on a page or a screen. If something is going away from us, we're going to represent that as an X. If something is coming towards us, we're going to represent that as a dot. I want you to think about an arrow, a stylized arrow, so to speak. The back end, if you were looking at the back end of an arrow moving away from you, it would look like something like an X. And if it was moving towards you, then it would look something like a dot. And that's how to remember these things. So if we have this setup right here, that means the magnetic field is coming out towards us because we see the dots. And notice we've got this loop that's represented right here. That's kind of like this scenario right here. And as time goes on, that loop rotates to be more normal or at right angles to the direction of the magnetic field. You could say that this would be like a cosine of 90. This would be like a cosine of 0, so to speak. Alright, so that's just another way to visualize what I was talking about earlier. Before we move on, there's one more concept I need to relate this to, and I want to talk about inertia, because Lenz's law, what we're going to be talking about, is conceptually similar to inertia. So one thing to remember about inertia is that it's a property of mass that resists acceleration, and the more mass something has, the more tendency it has to stay at rest if it's at rest, or to stay in motion if it's in motion. Think about it this way. If you had a dream where you pushed on an elephant, and you also pushed on a cat, because the elephant has so much more mass, it has so much more inertia, more of a tendency to stay at rest if it's at rest. And the cat, because it has such less mass, would have less of a tendency to stay at rest if it's at rest. So you could say inertia is a property of mass that resists acceleration. Alright, well, I do want to think about that concept that there are things that resist other things in physics, because Lenz's law is the tendency for an induced current to resist or oppose a change of the magnetic field causing the induced field. So let me give you an example of what it is I'm talking about. So this is our first example here, and I want you to think about what's happening to the external magnetic fields while we go from our initial position to our final position. So the external magnetic field inside this coil of wire right here is going to be increasing or decreasing. What do you think? Well, it's going to be increasing as it comes out towards us, so to speak. Alright, well, if there was a current that started flowing in this wire, either in this direction or in this direction, like I showed you with the initial animation, the question would be, how would it flow in such a way as to oppose that increase of magnetic field inside the loop? In other words, the opposite of coming towards you is what? Well, moving away from you, right? So the current is going to flow in this direction or this direction. We haven't determined which yet, but it's going to flow in such a way as to oppose the change in the magnetic field. So it's going to flow in a direction so that our magnetic field in the middle goes into the page or into the screen. And that's what Lenz's law is. So then the question becomes, well, what direction is the current going to flow such that there is an induced magnetic field now going into the page or into the screen? And this is where our understanding of the right-hand rule of magnetic fields comes into play. So let's think through how this works. Alright, I'm going to show you two examples here, and I want you to imagine your right hand and take your pen or your pencil, and you should do this like in class. I tell my students they should be doing this if they're taking a test or trying a problem with this. But I want you to think about, does the left example make more sense or the right example make more sense? So imagine this wire right here or this wire right here represents this wire right here. And notice we want a magnetic field that goes into the page in the center here. And the curl of the fingers of the right hand shows the direction of the magnetic field. So is the left example correct or the right example correct? Well, it turns out that the left example is going to be correct, and that's because the fingers are pointing into the page or into the screen underneath this wire that is shown right here. Just like this wire right here, underneath that wire you've got magnetic field going into the page or into the screen. Alright, let's do another one. So which of the two diagrams here do you think represents reality better? The top diagram or the bottom diagram? Well, remember, we want the magnetic field on the inside here to be going into the page or into the screen. And if you take a look at this bottom diagram is going to represent what's happening on the right side of this loop over here, because the fingers are pointing into the screen on the left side of the wire. So we're going to go with that one. Oh, and I do want to point out that the thumb is going to show the direction of the current that's involved. All right, so let's take a look and think about, well, what would be the correct drawing? This drawing over here or this drawing over here for the bottom section of the current right here? And again, remember, we want the magnetic field going into the page above the wire, so to speak. So which drawing shows the magnetic field going into the page above the wire? Alright, well, into the page above the wire is going to be this left diagram over here. And finally, let's take a look at the last two options that we have. Which diagram makes more sense, the top diagram or the bottom diagram? Well, hopefully you can see at this point that the bottom diagram makes more sense, and it should be consistent. If you are doing something like this, you should get all of them moving in the same direction. So it should be clockwise or counterclockwise. If you have, say, 3 of these that are moving clockwise, 1 counter, then you know that you've made a mistake. Let's do one more quick one as we wrap this up. So now we've got the magnetic field coming out at us. And I'm going to say, in all seriousness, please pause right now if you're interested in seeing if you have learned this material and see if you can figure it out. Use your pen in your right hand and see if you can figure out the direction of the magnetic field for this loop. Alright, so hopefully you went ahead and did that and you're able to test yourself. Let me show you the answers in a similar style to what we have done before. So this, remember, in the middle, those magnetic fields are coming straight out at you from the screen or from the page. And so this is what the current is going to be doing. From our perspective here, the current is going to be moving in a clockwise direction. And that's it for this lesson, although I'm going to go over Faraday's Law next. So please stick around. I'll put a link to that in the upper right. Have a great day. And please put a comment down below if you have any comments. Take care.